Look closely at this wire. Inside, there is an invisible reservoir of electrical energy, electrons waiting for a path to surge forward and do work. When we harness that electrical surge, we can translate it into tangible mechanical force. You can see the result in early consumer tools like this vintage metal drill. The scale translates perfectly. Looking at the drive belts and cooling fins of this heavy industrial motor, the exact same power conversion takes place. Whether you are boring a hole through wood or driving a massive factory floor, every application relies on a single, reversible physical relationship between magnetism and motion. In this schematic, a current-carrying wire between north and south poles experiences the Lorentz force, a physical sideways push. But a straight wire provides only one brief push before stopping. By bending it into a loop, opposing currents twist the wire exactly half a turn. There is a mechanical catch. Because the north and south magnetic poles remain completely static, the loop gets physically stuck after rotating 180 degrees. The magnetic forces are now pulling the loop apart rather than spinning it. To achieve continuous rotation, the direction of the electrical current must swap at the exact moment the loop gets stuck. The solution is a mechanical switch called a split-ring commutator paired with stationary carbon brushes. Here, the commutator rotates against static carbon brushes. Because the ring is split, the electrical contact physically swaps sides every half rotation. This constant reversal tricks the magnetic force into continuously pushing the loop in the same direction. The vectors flip, and the spin never stops. Mass-producing these motors meant mechanical power was no longer tied to a steam engine. It could be delivered anywhere a wire could reach. That is the essence of an electric motor. Electrical energy is the required input, and continuous mechanical movement is the resulting output. But the moment that motor starts spinning, a strange complication arises in the circuit. You now have a metal wire moving rapidly through a magnetic field. Whenever a conductor moves through a magnetic field, that movement naturally induces its own voltage. The spin itself starts pushing electrons. We call this back EMF. As the main supply pushes current in, a new arrow appears, fighting directly against your original power supply. You have likely experienced this in your own home. When a heavy power saw or vacuum cleaner first starts up, it draws a massive spike of electrical current, sometimes enough to dim the lights. But as the motor spins faster, the back voltage grows, chokes off that initial surge, and the machine settles into a much lower, steady current draw. Because this induction is happening internally, every functioning motor is effectively operating as a generator. We can prove this by completely removing the battery from our physical setup. Look at this diagram. If we attach a hand crank to the wire loop and manually spin it through the magnetic field, that mechanical force alone will compel the electrons to flow. This is the generator effect. We aren't supplying electricity to create motion anymore. We are supplying motion to create a flow of electrons, which we can easily capture to power an external component like this light bulb. The demand to capture that generated electricity grew rapidly. In this historical photo, you can see a woman operating a charging station to power an early electric carriage, relying entirely on generated current. A generator is structurally identical to a motor, just run in reverse. Mechanical work is the input and electrical energy is the output. This split-screen graphic gives us the direct comparison. On the left, we have a motor. Electrical input yields mechanical output. On the right, a generator. Mechanical input yields electrical output. Notice that the architecture inside both machines is identical. They both rely on a loop of wire sitting between magnetic poles. The only difference is the direction the energy is flowing. That simple reversal scales up to power the modern world. This image shows a row of massive hydroelectric turbine generators. Falling water provides the mechanical input, spinning the identical architecture we just saw to create the electrical backbone of our cities. If you are studying electromagnetism, mastering these machines simply requires tracking what goes in and what comes out. Electricity and motion are perfectly symmetrical, inextricably linked by the same physical laws that turn spinning turbines into the voltage at your wall outlet.